Wheatstone bridge. Wheatstone bridge is a electrical circuit which is used to measure the unknown resistance, and by connecting it so as to form a quadrilateral with three known resistances and applying a voltage between a pair of diagonally opposite corners. So the diagram shown here is called Wheatstone bridge. Here the four resistors R1, R2, R3, R4 are connected like shown in the figure, and here an battery is connected between the pair of diagonally opposite corners A and C, between A and C, which provides the potential difference to the electrical circuits, and it is called battery arm. AC is called battery arm, and galvanometer, a device used to measure the current, is called galvanometer, is connected between the points B and D, so it is called galvanometer arm. So this is the diagram of Wheatstone bridge. So mainly it is used to find the unknown resistance, any one of the unknown resistance, by knowing the three known resistances. So it is the practical, that is theoretical version of the bridge, meter bridge, theoretical version. So which gives the balance condition. By using it we can find the unknown resistance. So in order to find the balance condition of this Wheatstone bridge, we assume initially Ig equal to 0, that is current passing through the galvanometer is 0. So that thereafter the bridge is said to be balanced. So the current will flow in every amp will be equal. So for Ig equal to 0 means there is no current flows through the galvanometer. So Ig is the current flows through the galvanometer. So it should be 0. So for that, in order to keeping 0, B and D should be in equal potential. Then only no current flows through the galvanometer. So such that we are choosing the resistors, and we need a balance condition, that is R1, R2, R3, R4. So for that we are going to derive the balance condition. So initially we assume Ig equal to 0. So here by using them Kirchhoff's laws, first law we know. So if Ig equal to 0 means I2 equal to I4, we can say. The same way I1 equal to I3, because Ig equal to 0. So we can write from Kirchhoff first law, I2 equal to I4 and I3 equal to, I3 or I1 equal to I3. I1 equal to I3. So applying the Kirchhoff's second law, that is voltage law or loop rule. Consider a loop AB DA. So in the loop AB DA, in loop AB DA, so that is the loop AB DA. Here there is no EMF, so only the resistors. So only we calculate the voltage drop across the resistors. So we know the second law of Kirchhoff, the total algebraic sum of the voltages in a closed loop is 0. So here we start from A, B, C, A, B, D, A. So start from A, the voltage drop, the I2 R2 is taken as negative because it's the direction of current. So it is the potential drop. So minus I2 R2, and so Ig equal to 0 we know. So we can write 0 plus, so here potential drop I1 R1, it is taken as positive because we move from lower potential to higher potential. So we can write I1 R1 equal to 0. The sum should be 0. So I1 R1 equal to, we can write taking I2 R2 right side, so I2 R2. Then I1 by I2, we can write I2 taking left side, R1 taking right side, so R2 by R1. So this is equation 1. So from the loop ABDA we found I1 I2 equal to R2 by R1. So in the loop, consider second loop, in the loop CBDC. So here apply the Kirchhoff's second law. So we can obtain here from starting from C. So I4 R4 is taking, so against the direction of current, so taking minus, I4 R4, and Ig equal to 0 we know, and I3 R3, this is also we can write. So we start from here, and this is in the direction of the I3 R3, the voltage drop is in the direction of the current, so it is taken as minus, and here we is taken should be plus because we are moving against the current direction. So it is I4 R4 is positive and I3 R3 equal to negative. So I3 R3, so which is equal to 0. So we can write, taking this on other side, so we can write I3 R3 equal to I4 R4. So I3 by R4 equal to R3 is taken right side, so R4 by R3. So this is equation 2. We know that is I2 equal to I4, I1 equal to I3, Ig equal to 0. Since Ig equal to 0, I2 equal to I4, I1 equal to I3. So we can write I3 by I4 equal to I1 by I2. I1 by I2 equal to R4 by R3. Instead of I3 by I4, we are writing I1 by I2. So this is equation 3. Now compare the equations 1 and 3. So both are same, left side same. So RHS right hand side also same. So we can write R2 by R1 equal to R4 by R3. So similarly we write R taking reciprocal R1 by R2 equal to R3 by R4. So looking at the diagram, this is the balanced condition of the Wheatstone bridge. So balanced condition should be R2 by R1 equal to R4 by R3. So simply we can write, otherwise R1 by R2 equal to R3 by R4. So another way we can write, just exchange the corners. So we can write R1 by R3 equal to R2 by R4. Just exchange the corners. So we can write also this R1 by R3 equal to R2 by R4. The same way R3 by R1 equal to R4 by R2. Also R3 by R1 equal to R4 by R2. So in this way we can write the balanced condition. So this is called balanced condition. Balanced condition for Wheatstone bridge. So by using this phenomenon we can calculate the any one of the resistance, unknown resistance, by knowing the other three resistances. Now let us suppose we have an unknown resistance which we insert the fourth arm. So R4 is thus not known. Okay, then keeping the known resistance R1, R2, R3, sorry, R1, R2 in the first two arms, and R3 till the galvanometer, varying the R3 till the galvanometer shows the zero deflection. So now balanced condition is achieved. So in this case we know the formula R2 by R1 equal to R4 by R3. If suppose you choose as unknown resistance as R4, then by knowing all three, so we can write unknown resistance R4, unknown resistance R4 equal to, from this equation taking R3 to left side, so we can write R2 by R1 into R3. So in this way we can find the unknown resistance by using the balanced condition of the Wheatstone bridge. Next we are going to see meter bridge. So meter bridge is a practical version of the Wheatstone bridge because it applies the principle of the Wheatstone bridge. By using the balanced condition of Wheatstone bridge we can find the unknown resistance, given unknown resistance. So here a meter bridge is shown in the diagram. Simply it consists of a 1 meter length wire, length of 1 meter metal wire, which has the same uniform area of cross section throughout the length, and it is connected between the two ends of the metallic strips A and C. And the metallic strips have two gaps in which the resistance R and S can be inserted, and the between the ends A and C battery is connected, so for necessary potential supply. So and the galvanometer is connected between the points B and D, that is galvanometer is connected taken in between R and S, the resistance R and S, and the second end of the galvanometer connected to a jockey, so which is a metallic rod which is used to sliding over the metallic wire, 1 meter wire, to make the electrical connection. So this arrangement make the bridge circuit, Wheatstone bridge circuit, because A, B, C, D, so similar to the Wheatstone bridge, and here AC is the battery arm and BD is the galvanometer arm, so through which current can flow. So we have to make Ig, that is galvanometer deflection, to null, then only it is set to the balance condition. So by using L1, and it is called 100 minus L1, total length is 100 centimeters, so it is taken as 100 minus L1. So if we make to galvanometer 0, the jockey is sliding over the wire, and at a particular point it shows galvanometer null deflection, so it is said to be balanced condition. So here measuring the L1, we can find the four categories, the four resistances. By knowing S standard resistance and by measuring L1, we can also calculate 100 minus L1, and finally R can be calculated. Here R is the unknown resistance. Here R is unknown resistance which is to be measured, and S is known resistance. So initially known resistance connected in particular gap, and by measuring the length L1 and 100 minus L1, so we can calculate the R value. Here AB equal to is one of the arm equal to R, and BC equal to S, having the resistance S, and the gap AD has the resistance of R centimeter into L1, because in the resistance per centimeter is taken as RCM, so R centimeter, and the length will be L1, totally 100 centimeter, so L1 is taken as the resistance in this gap AD, so R centimeter, resistance per centimeter is RCM, so total for length L1 R centimeter L1, and similarly the gap DC or CD is written as 100 minus RCM into 100 minus L1, so similar to this, so it is taken as RCM 100 minus L1. So as we know the balance condition, for balance condition AB by BC equal to AD by DC. So we know the from Wheatstone bridge, Wheatstone balance condition, we know that is simply we can write AB by BC equal to AD by DC. So otherwise we can take AB by AD equal to BC by CD. So anyway we can write, so here AB by BC equal to AD by DC, here AB equal to R, so by BC equal to S, so R by S equal to, for AD equal to RCM L1 by DC equal to RCM into 100 minus RCM, so this is RCM into 100 minus L1, that is RCM L1 is the total resistance in between A and D, and RCM into 100 minus L1, 100 minus L1 is the distance between, that is the distance of CD, and resistance in this distance is called RCM into 100 minus L1. So RCM cancelled, so we can write R equal to, we should know the R value, so this is the unknown value which is to be measured, so R equal to, taking S to right side, so it goes to numerator. So S into L1 by 100 minus L1. So it's a simple formula. By using this we can find the R value. By keeping the S value we can find to move the jockey on the wire and particular position, it will show the null deflection. So then it is called balanced position. So at this position we know the formula. So here applying these values, so R equal to, we can like this. So simply for S value, for fixing X value we can find the L1, and we can measuring L1 and knowing S we can find the unknown value R. So the unknown value should be attached here. So R equal to S into L1 by 100 minus L1. So in this way we can calculate the unknown resistance. For accuracy we can change the S value. For changing varying S value, L1 also can be changed. For simply taking for different values of S, different values of L1, L2, L3 can be obtained. By we can obtain the, each time we can have the R value. By approximating, that is by taking the average value of R, we can calculate the nearly accurate value of the unknown resistance which has been inserted in the meter bridge. So this is finally we can calculate the unknown resistance.